Here with the lead researcher, Professor Hamish McGowan, a geographer from the University of Queensland, and he's going to talk a little bit about the processes we're measuring here.
Right, one of the uncertainties with respect to climate and hydrometeorology in a warming world is how the alpine areas are going to respond to increases in temperature as we move through this century. Most of the work that's been done to date has been based on modelling with one or two spot studies, particularly in the Northern Hemisphere, with very little conducted here in the Southern Hemisphere and most notably Australia, where we have a very marginal snowpack and a marginal alpine environment. By that I mean that the snowpack here is principally isothermal. It sits around 0 degrees all winter, and very subtle changes in energy, either from radiant energy, changes in incoming energy from the sun, or energy associated with advection of warm air over the snowpack, or even heat from the ground, can have a very significant impact on the snowpack. Namely, it can melt it away very quickly, or it can make it last longer through the winter, better for skiing. What we're doing here is trying to take away some of the uncertainty by making direct measurements. Some of the first direct measurements made in Australia of those exchanges of energy which control the character of our snowpack. How long it persists for, how deep it is, and how much water comes out of it as opposed to how much is lost to the atmosphere. Namely, how much water can you get from this snowpack, which then flows down the catchments into our reservoirs and ultimately down the Murray River, versus how much is lost back to the atmosphere. So the instrumentation behind me measures radiation transfers, so we're measuring directly how much energy comes from shortwave radiation from the sun, how much of that is reflected back to the atmosphere, as well as incoming long wave, namely from warm clouds, atmospheric humidity, but also the emission of long wave thermal radiation back from the surface. When we sum that up, we get net radiant energy, and that's the amount of energy which is present within the atmospheric system to then heat the surface and evaporate moisture, such as snow, from the surface back to the atmosphere. This instrumentation measures those radiation transfers, but it also measures the turbulent exchange of heat and moisture from the surface or to the surface from the air through a process called eddy covariance. So these measurements will enable us to quantify the energy required to melt the snowpack under different weather systems, to quantify how much water is lost to the atmosphere as opposed to that available to flow down our rivers into our catchments, such as the Murray, and then is available for hydroelectric power generation, irrigation and so forth. By doing that, we'll also have data which is absolutely critical to be able to validate or test the modelling studies that are looking at how the snowpack is likely to change in a warming climate. Modelling is only as good as the data that goes into it. You put rubbish in, you get rubbish out. All modelling must be validated through direct measurement, through real observations, real data. And as field scientists, that's what we do. We spend a lot of time out collecting data so that the modellers sitting behind the computers have something which is real, which they can either validate their studies with or actually tune their models. So they give us a more realistic projection of how the hydroclimate in areas like the Australian Alps is going to change through the 21st century.